Okay, for hello, hello.
Yeah, we hear you.
Thank you. I just want to make sure this where the audio is from. Interesting. Uh, Hello.
I just don't see the slides right now.
Okay. Um, I'm trying to figure out. Hello.
Yeah.
Thank you. I trying to figure out. We have some echo here in the classroom.
Okay.
Hello.
Yep.
Hello. Hello.
Yeah, I hear you.
Thank you. Hello.
Yep.
Hello. Hello.
Got you.
No, I think it's better. Yeah. Okay. Finally. Okay. For online student, can you hear me now?
Yeah, I hear you.
Okay. Perfect. Thank you. All right. Finally, we set it up. Um I apologize for the delay. Um so good morning everyone. Welcome back to SIE 433 and 533. This is our third lecture. In today's lecture, we are first going to recall the topics we covered in the previous lecture. Then we're going to introduce the most fundamental concept for data science to my understanding. We want to quantify the similarities versus the dissimilarities. Actually, to my understanding, for the entire data science, we're trying to find out the difference or dissimilarities between different data objects so that we can do the classification, we can do the clustering, we can find out why the phenomenon looks like that based on given factors, so on and so forth. Okay, so we're going to introduce the definition and the computation of the dissimilarities and the similarities, the proximity matrices, and also how we can quantify those dissimilarities as the different distance and some matrices. Okay. So in the previous lectures, we introduced the concept of a data object. Any entity, as far as it can be described by certain data, is named a data object. Okay, so people also call it a data point, an entity, an instance for probability theory, or a sample for statistical learning or statistical inference. In order to describe or model and data objects, we use a variable. For example, a data object can be a student or a bank customer. We use different variables to describe its feature. For example, the gender, age, major for students, right? So on and so forth. And we have different types of variables. We have nominal variables, ordinal variables, binary variables. We have a symmetric and asymmetric binary variables for those categorical features. We also have a numerical variables. And for the numerical variables, we introduce an interval scaled and a ratio scaled, depending on whether it has absolute 0, so on and so forth. Okay. And for numerical variables, we have a discrete numerical variable and a continuous numerical variables. For discrete, it can only take some discrete values, for example, the integers for count data, or sometimes we model a binary data with an discrete variable. For example, 0 stands for negative for a certain blood test, and 1 stands for the positive. And continuous numerical variables are something that we can measure and record the measurement as a continuous value. For example, the height, weight, dimension, like diameter of a certain cylinders for manufactured goods, right? Those are the different types of variables. We use models to model those variables. And when we have the data, we want to have a certain exploration of data. So that needs the method for data characterization. We want to see, or we want to quantify how the data look like. We have a numerical method, for example, the mean, the median, mode, quartile, and variance, so on and so forth. Mean, median, and mode used for describing the central tendency or the highest frequency of the observations. Quartile give us the position in the distribution or in the population or sample that we have a 25% smallest or highest, so on and so forth. Median is a special quartile, the second quartile, which means 50% of the observations are below that number, and 50% are above. It means right in the middle, according to the sorting result. Variance summarize the scatter or dispersion of your data. So we can visualize those concepts: central tendency, dispersion, highest frequency, the quartile, with the box plot. It is a graphical method. We have 5 points to define a box plot, if you recall, right? We have 2 quartiles, Q1, Q3. These 2 quartiles defines the interquartile range. And that stands for the middle 50% of your whole sample or whole population. We have a median right in the middle of the whole population or sample, which is inside that interquartile range, that box. So these 3 quartiles defines the box. And also we consider the minimum value and the maximum value as a whisker, if you recall, right? By excluding those outliers. The outlier stands for what? Stands for the observations that are 1.5 interquartile range away from the Q1 or Q3 when it is too small or too big, right? Those are the way we can define the box plot. So no matter whether it's a numerical method or graphical method, we just want to have exploratory analysis of the data, like a first glance of your data, how it looks like, right? We want to have those kind of understanding. So when we want to study more about the data, we want to, for example, find out the classification, clustering. If you recall, we have one example. We show the scatter plot of the iris, right? We consider their sepal length or sepal width, petal length or petal width. From those scatter plots, we see those each individual dots in that plot is or represent an iris data object, that flower. And from those scatter the plots, we see those plots are clustered into 2 groups. And that is a fundamental graphical way for us to find out, okay, how we can have a clustering analysis. That is very fundamental way to differentiate different types of data objects. So those distance from the dots give us an idea, okay? We see some cluster, those group of data objects or data points are closer to each other. And their within cluster distance is higher than the cross cluster distance from the data points from another cluster. That's the fundamental way for us to see or to visualize the dissimilarities or difference between different data objects. That is actually the foundation for data science. And the basic idea actually is the so-called similarity and dissimilarity. What is a similarity? It is a numerical measure of the degree to which two data objects are alike. If they are similar to each other, then that we can have a numerical measure of that similarity. The higher the similarity, when the two data objects are more alike to each other, okay? And this similarity, usually we create a quantity that is between 0 and 1. 0 means no similarity, totally different. 1 means they are identical, okay, almost identical. And dissimilarity, just on the contrary, it is a numerical measure of how the two data objects are different. And lower the dissimilarity, the more different the two data objects will look like, okay? And the minimum dissimilarity is often 0, means the two data objects are the same, okay? And people use this proximity refer this similarity or dissimilarity, okay? So proximity, from the definition of this word, I searched the MW Webster dictionary online. So this proximity means give us a certain sense of the distance, okay? Actually, statistical analysis is talking about distance. Probability is talking about distance. I believe many of you have already heard about the statistical distance. I don't know how many of you have heard about this concept. How many of you know the z-test? Right. Can you write down the z-test statistic? Z-test is X bar, that is your sample average, minus the target mean. We take absolute value over sigma over square root of n, right? That is a z statistic, or actually we should replace, we should replace this s by sigma. That is actually the z statistics. And this is the distance. X bar is your sample mean. Mu0 is your target mean. Absolute difference is the distance between these two quantities. What is sample average? That is the center of a group of data objects you observe. And we divide this distance by the scatter or the variance, standard deviation of your sample. So this is so-called statistical distance, right? These statistics, we have seen distance before. For data science, we have a more definition of the proximity or more interpretation of the distance, not just the statistical distance, okay? So that's the proximity. And so when we are dealing with multiple data objects, we use the data matrix to organize the data. And we have talked about the table or array in the previous lecture. So in today's lecture, we are going to give a more formal definition of a data matrix. So we have n data objects. Each individual data object is modeled by p variables or p features. And so we can organize a data matrix according to that setting. We have n data objects. Each row in this data matrix represents a data object. So each row is a data object. Then each column is a feature or variable. So we have n data objects, and each of which modeled by p variables. So we have n minus p matrix. That is a dimension of the data matrix. So usually we would, if we name this matrix as big X, so this X we can give subscript n times p. That's the dimension of this matrix. Okay, and in our lecture notes, when it is printed, we use a bold capital letter to denote matrix. We use bold font. But when I write, I will use an underbar to denote it is a matrix or a vector. This is our notation mechanism. Okay, I hope you can get used to it. So given a data matrix with n data objects, we can calculate each pair. We can calculate the dissimilarity of each pair of data objects. So how many dissimilarity we can have? We can have n 2 out of n, that combination of dissimilarity coefficients, okay, the quantities. So we organize those dissimilarity coefficient or index or quantity into a model as well. That is a dissimilarity matrix. So this is a symmetric matrix because the similarity between A and B should be the same as the dissimilarity between B and A, right? So this is a symmetric matrix, which means if we use D to denote the dissimilarity and D parentheses I J means the dissimilarity between data object I and data object J. So this is the dissimilarity index or quantity between the data objects I and J. It is the same as D J I. Okay, so we put the dissimilarity between two different data objects on the diagonal elements or diagonal component of this matrix, dissimilarity matrix. For the, off diagonal. On the diagonal elements, we put 0 there because those are dissimilarity between the first data object and the first object. What is the difference between you and you? You're identical, so dissimilarity is 0. That's why all 0 on the diagonal elements. Off diagonal will be the dissimilarity between two different objects. If you have n objects, data objects, this matrix will be n by n. So if we use D to denote it, then this is a D matrix with dimension n by n. Okay, that's how we organize those data. So throughout this semester, we're going to use a lot of like matrix vectors that's linked to some linear algebra basic knowledge. When we work more on it, you will get used to it. Don't worry too much. Okay. So now we talk about the distance or dissimilarity. You can use interchangeably. The dissimilarity, which is a dissimilarity measure between the data object I and J. So we use this D parentheses I and J to denote it. This distance must satisfy 3 properties. It's not just any arbitrary quantity. It has to satisfy 3 conditions. First, it is a positive definite. The distance or difference between 2 data objects must be positive. Okay, you have to define this quantity to denote this the difference. Okay, and it can be positive when the 2 data objects are different from each other. There's at least some difference. It is equal to 0 when these 2 data objects, at least when modeled by the given variables, are the same. For example, two of students in this class, okay? If we only consider the gender, department, major, we may have multiple students are identical to each other. So those dissimilarities only equal to 0 when there are two different data objects. Their dissimilarities equal to 0 only when given the variables we model the data object, they are the same. Okay, and so if you cannot differentiate them, it doesn't mean they are the same. It only means with the variables they are the same. Only in the dimensions that we model them, they are the same. Okay, so positive definite. Symmetry. So I mentioned just now, the difference between I and J is the same as difference between J and I. So it's symmetry. And triangle inequality. The difference between, or distance between I and K is less than or equal to the distance of IJ and plus the difference of J and K. It's just like a triangle, okay? For all objects, I, J, and K, for any three arbitrary different data objects. And the distance definition must satisfy these three properties. Otherwise, it is not a qualified distance matrix. Okay. So later we are going to introduce different types of distance measure. You can see some of them should not be used as distance because it doesn't satisfy this triangle inequality. We are going to give some examples. Okay, and so we can calculate the difference or distance between two data objects according to or with respect to different variables, and we are going to introduce those regularly used proximity measure or distance measure for different types of variables. Right now, we need to recall the different types of variables we introduced in the previous lecture. First, nominal variables. We may take two or more states, right? What are the nominal variables? Categories without a sense of a ranking, right? Color of hair, white, black, blonde, right? So that's a different color. And those color has no ranking, right? So those are the nominal variables. We may have two or more states. And so the first method for us to give a distance measure of two data objects modeled by nominal variables is this. First, we have M as the matching variables. It means we have multiple data objects that we have two data objects, both are modeled by multiple nominal variables. Okay, so we can have a number of matching variables as M and the P as a total number of the nominal variables. And the distance is defined as the P, the total variables, minus the number of matching variables over the number of total variables. So it's kind of like a ratio, right? This is a ratio of identical nominal variable values. First method. Second method is we convert single multi-state. Actually, we convert a series of binary variables. For example, we have a multiple state of a single nominal variable, like a hair color, red, yellow, blue, green. So we can have one binary variables for red. If one data object has a red hair, so it is 1. Otherwise, it is a 0. We have a multiple digits, or we have multiple binary variables to model a multi-state nominal variables. That is another method we can compare two different variables modeled by nominal variables. Okay, this is the first one. Then for binary variables, if we model a data object with binary variables, for example, the test result, right? Positive and negative, so on and so forth, we use contingency table. Okay. If we have a P binary attributes or P binary variables, the contingency table matches the mismatch between the two objects I and J. So for different columns, we have 2 columns and 2 rows in this contingency table. 2 columns are for object J. 2 rows are object I. So M00 means the number of variables for both data objects have a 0 as a value for the binary variable. Okay, number of variables where I equal to 0 and J also equal to 0 means they match to each other. And M01 means I has 0 for those variables, binary variables. J has 1. M10, M11 defined similarly. Okay, so the total number of binary variables for modeling these 2 data objects is equal to the summation of all these numbers, which is we define it as a P. Okay, and that's the total number of binary variables we use to model the data objects. The different proximity measure the symmetric and asymmetric binary variables will be different. Let's see. For symmetric binary variables, we consider both 0 and 1 as the same, as important as each other. So they are the same, consider the same for both 0 and 1. In that case, all those 4 numbers matters. And this is how we define the dissimilarity or distance between the 2 data objects that are modeled by all the P symmetric binary variables. This, for example, gender is 1, right? Symmetric binary variables. But in many cases, especially for healthcare, for some other cases, asymmetric binary variables are the most often seen variables. For example, test result, positive, negative, right? For some symptom, positive, negative. And for application for certain, like a bank account, approval or denial, they're different, right? Meaning different thing for the applicants. So in that case, we should define this distance in this way. What's the difference? What's the difference between these two for symmetric and asymmetric? Numerical values, same, right? Because we care about the difference. But the denominator difference, what is missing is M00. The 2 data objects are the same for negative results. Why we don't care it? Because negative result means no more treatment, right? No more follow-up. It's not so important. So even with these 2 ratio, we care or don't care about both negative. That's the difference. For asymmetric, because negative or 0 means less important, so we don't really care about it. So we don't even want to include it into this denominator. Okay, so that's the difference. And for data science, people almost always put 1 to something, to some result for the binary result, to some results that are more important, like positive, right, pass of a certain exam, get approved for some application, so on and so forth. Okay, so those more important outcomes are assigned a value with 1. Then let's look at this example. So here we have 3 patients. And for each patient, we have different variables to model them, attributes. Okay, first, the name. What is the type of this variable? Name, nominal. Why nominal? They're different, and there's no ranking, right? We cannot say, okay, Mary is better name than Jack, right? That's nominal. What about gender? It's binary, symmetric binary. Okay, fever means does this patient have a certain symptom of like a fever? Yes or no? Yes means positive for the fever. Is it so this fever, is it symmetric or asymmetric binary? Asymmetric, because fever means more, right? More important phenomenon or a symptom to treat. Cough, yes, negative or positive. Test 1, test 2, series. We can see from this data type, this data table, we have 3 data objects. So we have 3 rows. We have 7, 8 columns. ID, we don't consider it as a variable, okay? We have 8 variables, 1 nominal, 1 symmetric binary, and 6 asymmetric binaries. So we have 3 by 8 this matrix, okay? And so now we calculate the distance based on the asymmetric binary variables. First, the difference or the distance between Jack and Mary. We only consider the asymmetric binary variables. M01 means this means Jack as negative and Mary as positive. We have that kind of do we have that kind of a case? Actually, M01 is equal to 10. M10 means Jack is positive. Jack is positive, and Mary is negative. That is equal to 0. Right? From this 6. And M01 for Jack is negative, Mary is positive. We have one case. We have this case, right? That is 1. And for M11, so Jack is positive, and Mary is also positive. We have this one, right? 2. So totally, how many variables do we have? 6. But we only consider those non-0, 0 results. So that's why we have this result. Okay? So that's the distance between this Mary and Jack. Then we consider, for example, this one, the Mary and Jim. So for Mary is positive, Jim as negative, Mary positive, Jim has negative, this one, this one. So that is equal to 2, right? So M10 is equal to 2. Then for M01, means Mary as negative, Jim as negative, this one, so just 1, right? Then M11, we have this fever, it's just 1, right? So the overall, you can add up 1 plus 2 over 1 plus 2 plus 1. So without considering both negative cases, this Mary and Jim has the largest, has the highest difference, right? So that's what we can see. All right. So this is the distance for asymmetric binaries. That is more important than the for the symmetric binary variables. Do you like this idea? By hand for this simple case, right? I made a mistake at the beginning. You like this? To do this by hand? I don't think so. That's why we use computer to learn it, right? If we can build some code and have the computer to read the results and calculate just the, without any effort, right? That's why we use computer to learn rather than, people to do it by hand. Okay, this is for dissimilarities or distance for asymmetric binary variables. Here we introduce one similarity matrix. It's just the difference from the distance. We care about how similar the two data objects are close to each other, are the same, are similar to each other. Okay, we call it Jacquard coefficients. You can see for asymmetric matrix, we care about how the two data objects share the same positive. We don't care about the same negative, right? This is for asymmetric. Only the similar result or same result considered for the numerator. We don't forget, we don't consider the M00, means two data objects share the same negative result. We don't care because it is not important, right? This is Jacquard. So we look at this result, this example. The Jacquard, you can work on this yourself, right? So we list all 3 data objects. They are modeled by this symmetric and asymmetric binary variables. We only consider those asymmetric variables. Gender, symmetric, right? The food, good or bad. Good, V means good, N means bad, I believe. And caste, education, hobby, job. The last 5 are the asymmetric binary variables. You can work on this result to see whether you can get the same numbers, okay? And also J12 and J21, this for this Jacquard distance. they are symmetric, right? So similarity between 1 and 2, the same as the similarity between 2 and 1. And we can see that this similarity, the second and the third data objects, Ram and Tommy, they are totally what? Different. Are they? Gender different? Food negative. Negative means it's not important, so it's not considered, right? So it's not considered, even though they are the same. We forget about it. It's not important. Caste, they are just they are different. Education different. Hobby, job, they are different. But for this same food result, even though they are the same, but because it is the unimportant result, so we don't consider it. That's why we say these two are totally different. Totally different. So similarity is 0. And the distance for numerical variables was much easier. We have used this before in many other courses actually already. We call it Minkowski distance. That is a general definition of the distance between two numbers. Between two numbers or two data objects that are both modeled by numbers or numerical values. It is the summation of distance between two data objects. Here, xik is the variable, the numerical variable xk for the ith data object. So the first subscript is the ID of the data object. The second subscript k is the index of the variable, and x is just a representation of the variable. Okay. So for each individual data object, we have a p with reserved p to stands for what? The number of variables. We assume that all those variables, p variables, are numerical in nature, numerical variables. So k means the kth variable out of these p numerical variables. Okay, so each data object has p numerical variables, and we call this Minkowski distance the LH norm. We are going to hear about this norm term a lot throughout this semester. Okay, and so first, this Minkowski distance satisfies the three properties. It is the most generic metric to evaluate the distance between a pair of two numerical data objects. But it may have different interpretation with different h, right? So for each individual variable, we compare the distance between the two data objects, and we take an absolute value of it, and then to the power of h, and we sum up with respect to all the p variables. We sum them up together, and we take 1 over h, that exponent, to get this final distance. That is the most generic distance for numerically described or modeled data objects. Let's take a look at h equal to 2. Okay, so for I and j, we only have 2 numerical variables. And we take h equal to 2 as well. For xi1 minus xi2, absolute value, then we square it, right? So h is equal to 2 plus xi2 minus xj2, take absolute value, square it. And we have this summation. What we did next, we take a square root. That's 1 over 2, right? What is this? If we have x1 as one dimension, x2 as another dimension. So this is a data object I. This is another data object J. What is this Minkowski distance when h is equal to 2, or we call it L2 norm? What is this? We have the x1, 2 minus xj1 minus xi1 minus xj1. Sorry. xj1. That's this green distance, right? And with respect to the second variable, quantitative numerical variable, xi2 minus xj2, that's this distance. And square them together, and square them and add them up together, we got what? The square of this distance between these two variables, right? And we take a square root of it. We got the distance between I and J. What is that distance? Euclidean distance. That's L2 norm. L2 norm is actually the Euclidean distance. Okay. And then here we have a more interpretation of the Minkowski. We call it special case of Minkowski distance. First, when h is equal to 1, a special name is so-called Manhattan distance, L1 norm. L1 norm, by interpreting that general definition of Minkowski distance, is the absolute distance between the two data objects according to the first variable, second variable, we add them up together. That's L1 norm. Okay. For example, the Hamming distance is a number of bits that are different between two binary vectors. This can be even used for some binary vectors. Okay. And second, h is equal to 2. I explained just now. It's a Euclidean distance, right? This one. In high dimensional space, we have a p. In two-dimensional space, we can explain, plot it on the paper, right? And when h is equal to infinity, it's a supremum distance, or we call it h infinity, L infinity norm. Basically, that is equal to max of absolute distance according to all the p dimensions. Okay? We forget about all the other dimension. We only look at one particular dimension that gives us the highest value of the difference between the two random variables, the two objects. Then that's the so-called L infinity norm. The maximum difference between any component variables or the vectors. Okay, that's the different interpretation of this Minkowski distance. Which one we use the most? That is one, the Euclidean distance. And if you can plot the data object or transform it in a certain form so that you can show this Euclidean distance, it means you can visualize the difference no matter how you do it on a paper and show it to your customer, you're done. That classification clustering results will be understood by your customer. That's the whole, ultimate objective for any data science. But that's different. For example, if you have an image of a dog and another image of a small pig, they could be quite similar. But can you model them in a certain way so that you can use the Euclidean distance to show the difference? That's deep learning or machine learning or visual or computer vision, what people are trying to do. Okay. So by looking at this Minkowski dissimilarity or distance value, we can work on this example. So in this case, how many data objects do we have? 4, right? So 4 points. Defined in this, we call it Descartes coordinates. We have a 2 dimension, 2 variables. We call it 2 dimension, right? And for example, the first data object, the coordinate along the first dimension is 1. Along the second dimension is 2. So this is the first data object. And similarly, we can plot the position of all the 4 data objects. So first, let's look at the Manhattan distance of these 4 data objects, right? We have a 4 by 4, that's a distance, right? N by N. N is 4 and P is 2, right? This is our data object. So for distance matrix or dissimilarity matrix, we have N by N, that is a 4 by 4. Fortunately, all the diagonal elements are 0, right? Because the distance from me to myself is 0. Then let's look at x1 and x2. The Manhattan distance L1 norm, summation of absolute distance according to different coordinates or different dimension. So for first dimension, x1 and x2, according to the first dimension, that result is absolute value 3, or actually be more strict. That is absolute value 1 minus 3. First and second. And we consider the second dimension, absolute value 2 minus 5. So the overall distance, Manhattan distance between the first 2 data objects is 5. Okay, and for 2 and 3, 2 and 3. So according to the first dimension, it is a 3 minus 2. Second dimension, 5 minus 0. The distance is 6. Okay, so according to Manhattan distance, the distance between x1 and x2 is less than that between x2 and x3. Okay, and for x3 and x4, that will be 0, 2 minus 4 plus 0 minus 5. This result is even higher, 3. So according to Manhattan distance, the difference between 1 and 2 is less than that of that between x2 and x3, and smaller than that between x3 and x4. Okay, of course you can figure out those values. That's not difficult, but tedious. Okay, so Euclidean distance. Of course, the diagonal elements are all 0. Then for x1 and x2, square root of 1 minus 3 square plus 2 minus 5 square. And you can calculate the distance, the Euclidean distance. X 3 and 4. That is a 2 minus 4 square plus 0 minus 5 square. And you can calculate the result. Okay, they're not difficult. Visually, we can see their difference. So by just taking a look at this visualization, which two has the highest distance? X3 and X4, right? X3 and X4. But in terms of supremum distance, they actually give us a different result. I'll use the blue. Horizontal axis. So for supremum distance, if we consider the distance between x1 and x2, we have we have to compare the two absolute distance with respect to x1 and x2. Or with respect to x1, the first data object is 1 minus 3. And the other one, x2 dimension, is 2 minus 5. So 3, right? So this give us 2. And this 2 minus 5 absolute value give us 3. So which dimension give us the highest or largest or greatest distance along x2 dimension? So the result is 3. What about x2 and x3? Second and third. So which dimension give us the largest distance? One is on the top, the other one is at the bottom. So of course the second dimension. What is the difference? That is 5. And that for x3 and x4. Again, you can see x2 and x4 is on the top. X2 is on the bottom, x3 is on the bottom. So the maximum distance according to different dimensions, the second dimension gives us the largest distance. So you can see visually, x3 and x4 has the largest distance because that is the Euclidean distance. But for supremum distance, we only care about one particular dimension. So x2 and x3 at the same supremum distance between x3 and x4 because their height difference are the maximum. Right, so they have the same supremum distance, but in terms of Euclidean distance, you will see that they are different. Okay, for Euclidean distance, x2 and x3, you have 3 minus 2 square plus 5 minus 0 square. Of course, it will be smaller than that between x3 and x4, right? But that's a different Minkowski distance. Here we give some example on how you can identify some of the distance matrix are good. Some of them are not qualified for distance. For example, here, we have two data objects, different data objects modeled by numerical variables with p dimensions. Okay, the first one, we call it D1. Okay, between data object I and J, it is a maximum of xik or xjk according to all the k dimension. So what is the difference between this distance and the supremum or L infinity norm? This is L infinity norm. Which one? This is thought it is a valid distance. Why this is not? Is it possible for a certain maximum value that are negative? It's possible. So it violates this particular criteria or condition. Okay. And this L2 is more similar to this L infinity norm. The difference is there's no absolute sign for this max. Again, potentially non-negative violation. Okay, this is it could be negative. So the third one is the Euclidean distance. This is good. This is bad. And also for the first one, the maximum of xik and xjk, inversely, it could be just different. So symmetric condition is violated as well. Okay, then let's talk about the last one. Instead of looking at the maximum absolute distance according to different dimension, here we use a minimum. Is it good? Why it is not good? Which one do they violate? Okay, let's look at this example. We have x1, the first data object, the second data object, and the third data object defined in this two-dimensional space. What is D12, D13? According to this definition of distance. Minimum between x first and the third along two dimensions. at least we know it is positive, right? Because both x1 dimension and x2 dimension, x1 and x3 are the difference are positive. This is a positive. Then what about D12? What is the minimum distance according to this? That is 0, right? Because along x1 dimension, their minimum distance, absolute distance is 0. What about x2, D2, and 3? Because they are horizontally on the same line, so their minimum distance is 0. So do you still recall the triangular property, inequality? So D13 must be less than or equal to D12 and plus the D23. But here we have a D13, it's positive. D12 and D23, sum them up together is 0. So it violates this distance, this triangular inequality. So this is not a qualified distance matrix. I hope you can understand how we understand this too. Okay, this can be positive and satisfy the symmetric, but it violates these triangular inequalities. Okay, and here we have ordinal variables with rank, right? Nominal values or categorical values with rank. And then it is important to consider the order between different possible values for an ordinal variable. So in that case, we can create a numerical value for the ordinal variables. We replace the value of xik. Don't forget, it is a category, okay, with its rank. Rank can be 1 to mk. K is the index of the variable. M is the number of a possible state. Like for student, undergrad, master, PhD, so totally we have a 3. So 3 ranking, and this rank can be 1 for undergrad, 2 for master, 3 for PhD, for example. Okay, and we map the range of each variable onto 0, 1, that range. Okay, and we're replacing the rank of the case of the ith object with respect to the value k, variable k, be the ith object and the case variable. In that case, the quantity of the ith data object with respect to ordinal variable k can be modeled as this. Okay, so this captures the dissimilarity using the method of a numerical variable. I think consider the time. Let's skip it. We will work on it in the next lecture. Okay, next week. There's no homework for the first for this week. But we are going to have a bigger homework for the next week. Okay, thank you. That's all for today. Thank you.